Hi everybody, here we are talking about lesson 8-5. We're going to talk about the quadratic equations and differences of squares. Differences of squares. Remember, we've already talked about something that looks like if I have I'm going to make a problem up. I have 4 minus x times 4 plus x. You already know what that looks like. There's a shortcut, isn't there? I could FOIL it out, but what's going to happen to the middle terms? Since these two sets of parentheses are exactly the same except for the sign on the second term, those middle terms will always cancel out. So anytime I see this happen, I know I can write down 4 times 4 minus x times x. So it's going to be 16 minus x squared. That's actually setting up exactly what we need to do today, because now this is going to be what we start with, and we need to factor it back to get that. And we know that if it's going to be a perfect square and a perfect square with a minus sign between them, that we can factor it into something that looks just like that. So let's do an example. I am looking on page 499 at letter C, 1C, where we have 27g cubed minus 3g. Now don't forget, what you want to do every time you can is factor out a GCF. So always look for that GCF first. What is the GCF here? With this problem, the GCF between 27 and 3 is 3, so I'm going to write down a 3. And a g cubed and a g, the GCF is going to be g. So what do I have left? 9g squared minus 1. A few students are forgetting to write down the GCF. They're just writing down the stuff that is left over. And that's not correct. When you're factoring out, I've got to see what all the factors are. Okay, so make sure you write down your GCF and then put whatever's left over in parentheses behind it. Now I am looking for factoring, and since the whole point of this lesson is to learn this difference of squares, I want to see, is this a perfect square? And it is. You could write this down as 3g times 3g squared, right? Minus, that's what makes our difference, 1 squared, right? And now we can clearly see that we have a difference of perfect squares. And that means we know that it's going to be 3g plus 1 times 3g minus 1. And that's how we factor our difference of squares. Couple more examples if we can find something. I'm going to look at, let's see. That one was letter C. Let's do 1B, the same page, where we have 64 g squared minus h squared. Is this a perfect square? Well, we can write that as 8g quantity squared minus h squared. Now it looks like a perfect square. Is this a perfect square? Yeah. Now another thing that you can look for is, what is the square root of 64? The square root of 64 is 8. The square root of g squared is g. So if I put that whole thing in parentheses and square it, do I get that back out if I multiply it? I sure hope I do. So now I've got a perfect square minus a perfect square. That means I know how to factor it right away. It's going to be 8g plus h and 8g minus h. And we're factored. That's it. Pretty easy. Every once in a while you're going to run into something that is prime, something that cannot be factored at all. So if you try and you just can't get something to factor, it's a possibility that the answer will be prime. Okay, so remember, this one is not prime. This is factored. But sometimes you're going to get an example where something is prime. And I forgot to talk about that at the last lesson, so I'm going to just flip back really fast to page 495, and we're going to look at something like example 3, where we have 4x squared minus 3x plus 25 plus 5. Now we want to find two numbers that multiply to 20 and add to negative 3. So if we look, let's see, 20 is going to be 1 times 20. When I add that's 21. That's not any good. 2 times 10 add is 12. 3 doesn't go into 20. 4 times 5, and I add that, that's 9. That's not what I need. Or let's see, I've got a negative 3 over here, so maybe, well, that's not going to work. I could, if I make them both negative, like make negative 4 times negative 5, that would be a negative 9. You know, it doesn't seem like there's any way that I'm going to be able to get this negative 3. So when this happens and you go through all the possibilities of what's going to happen here, then what you can say is that there is no way I can factor it, and the answer for that kind of problem is prime. Let's do 3a. 3a says 4r squared minus r plus 7. We're going to look for something that multiplies to 28 and adds to a negative 1. 28 is, let's see, well, I'm going to have either both positive or both negative. So let's go through both negative. I've got 1 times 28, which is not going to give me a negative 1. 2 times 14, which is going to give me a 16, which is not a negative 1. 4 times 7, which is 11, is still not it. 5, 6, 7, then we're back to 7 times 4. So this one is also prime. Let's do one more example. How about 2x squared plus 3x minus 5? That, when we factor, we're going to look for something that multiplies to a negative 10 and adds to a 3. Multiplies to negative 10. Let's see, that's going to be one of them is positive and one of them is negative, since I multiply to a negative 10. When one of them is positive, let's see, 2 times a negative 5 would be, when I add that together, I get a negative 3. Or a negative 2 times a positive 5, which is a positive 3. That's the one we're looking for. 2x squared minus 2x plus 5x minus 5. 2x, oops, sorry, yeah, 2x, I've got an x minus 1 plus 5 times x minus 1, and then I have x minus 1 times 2x plus 5, and that's how we factor out this one. This is our answer. This one is not prime. Okay, so I hope that's all coming clear as we practice those a little bit more. Let's move on to section or lesson 8-6, which is kind of like the difference of squares thing that we were just talking about, but this time we're calling it perfect squares. And you remember before when we were multiplying and we had x plus 2 times x plus 2, something times itself. And we FOIL that out, we get x squared plus 2x plus 2x plus 4, or x squared plus 4x plus 4. Or if you remember the shortcut, you could come straight down here, right? You could go straight there if you remember the shortcut, since we're multiplying the same thing by itself. Then we can get x squared, and then we're going to do the inner one, 2x, and just double that, so it becomes 4x, and then the plus 4. So again, just like everything else we've been doing in Chapter 8, what we're going to be given with is that this is the starting point, and now we have to figure out how to factor it. So that is our starting point. I'm sorry, that was off your screen, wasn't it? Oh, sorry. So if we have the same thing times itself, our shortcut is going to be x squared plus 2x doubled, so that's 4x, plus 4. Now we're going to start with this, and how do we go backward? Well, what we look for is if this term is a perfect square, and this term is a perfect square, and the middle term is this square root times this square root times 2, then it's going to be something that looks like this. Let's do an example so you can see exactly what I'm talking about here. Let's do Letter 1A on page 506 under the Check Your Progress, where we have 9y squared plus 24y plus 16. Is this a perfect square? Yes, that is the same thing as 3y squared, right? Is this a perfect square? Well, that's the same thing as 4 squared. So yeah, 16 is a perfect square. Now, if I take this square root, which is 4, and this square root, which is 3y, I get 12y, right? 12y. So that's just this one times this one. And if I multiply that whole thing times 2, am I going to get that 24y that I started with? And if the answer to that question is also a yes, then I know that I can factor it as 3y plus 4 times 3y plus 4, or another way of writing exactly the same thing is this, 3y plus 4, quantity squared. I want you in your book to try to factor 1b. See if that one works with the same thing. So you pause the video and factor 1b. Here I go solving 1b. We have 2a squared plus 10a plus 25. Okay. Is this a perfect square? Is this first term a perfect square? We've got the a squared, but that 2 is not a perfect square, is it? So this one actually is not perfect squares, and so we can't factor it with the same shortcut that we've been doing. Okay. Let's try another one. Let's look at page 507, 5x squared minus 80. 5x squared minus 80. So should we answer our questions? Is this a perfect square? Oh, but wait a minute. We always are supposed to ask about the GCF first. So let's factor out our GCF if we have one. What's the biggest number that goes into both of these? The biggest number that goes into both of these? 5. So that means I write the 5 down out front, and I'm left with an x squared. 80 divided by 5, let's see, 80 divided by 5 is, does anybody know? 16. Okay, 80 divided by 5 is 16. So this is exactly the same as this, it's just that we factored out the 5. If I multiply this 5 through again, I should get that first line back. And I do. Now I can look at the stuff that's inside the parentheses and I can say, is this something that I know a shortcut for? Well, do you? Do you know any shortcuts? I'm seeing a difference here. So is it the difference of 2 squares? Yes, indeed it is. So if it's a difference of 2 squares, then you know right away what the answer is. I hope. Okay. Let's do another example. How about letter B on the same page 507? 9x squared minus 6x minus 35. Look for that common GCF. Is there anything that is common to all three of these terms? 9 and 6, maybe a 3, but 3 doesn't go in there. 2 doesn't go in there. So the GCF is 1, so factoring out a 1 is not going to help us very much. Is it a perfect square trinomial? What is the square root of this? Well, that would be 3x, right? 3x squared minus 6x, and now the square root of 35 is not available, so this is not going to help us. It's not a perfect square trinomial, so never mind there. Let's see. What is 9 times 35? Well, 10 times 35 would be 350, right? So 9 times 35 must be 341. No, that's not right. I'll do it the long way. 35 times 9 is 45. 27 and 4. That's better. Yeah, I'd subtract 35, not 9, right? Okay, so we want two numbers that multiply to a negative 315 and add to a negative 6. Let's see, what can we figure out about that? Multiply to negative 315. How about, let's just guess 15 times 21? Oh, but one of them has to be negative, so, and this is a negative 6, so I'm going to make that. When I multiply those, I get negative 315, and when I add these, I'm going to get a negative 6. That's pretty cool. This is because I practice a lot, but sometimes I have to go through several iterations. So if you didn't see that as quickly as I did, don't worry about it, and just keep trying through all of the possible numbers you get until you get something that works. So we're just going to write this down as plus 15x minus 21x minus 35. Again, if I add these together, I just get that negative 6, right? So now, out of my first two terms, I get a common factor of 3x, and then I'm left with 3x plus 5, and then minus 7. And when I factor out a negative 7, I'm going to get a 3x plus 5. So then we have a 3x plus 5 times 3x minus 7. On this one, there wasn't any shortcut, that we just had to do this one the long way. How's that work for you? Lots and lots of things that we can practice. One thing that happens a lot when I'm doing this kind of work is that we'll have something that has repeated factors. Something like, oh, let's look at 9x squared minus 48x equals negative 64. Now, when it's equal to a negative 64, we really want to make it equal to 0. So we're going to move that over. 9x squared minus 48x plus 64 equals 0. Do we have anything that might be one of our shortcuts? It's not a difference of two squares, but this is a 3x squared, right? And this is a plus 8 squared. And 8 times 3x is 24x. And it's a positive 8, but it's a, don't you wish you could just, that's not a 4, that should be a 2. If this were a positive 2 times all of this, then we could use our square, or our perfect squares thing. But in this case, the sign is different, which means that we can't use our perfect squares trick. So we're going to have to find two things that multiply to, oh, hold on. Did I write something down wrong? Actually, that will work. Sorry. This is 3x squared minus 2 times 24x plus 8 squared equals 0. And the reason this works is because if these are both negative, then they will make a positive third number over here, which is actually okay. I was having a moment. So we can actually factor this using our shortcut method of 3x plus 8 times 3x plus 8 equals 0. And actually, in this one, because this has to be negative, it's going to be a 3x minus 8 and a 3x minus 8. And the reason it has to be minus is that when I add them together, I have to get that negative 48. Even though it's multiplied to a positive 64, they have to add to that negative 48. Now, when I have this happen and it's equal to 0, remember we can use our zero product property to say, well, I've got this number which could be 0 or this number that could be 0. So that's 3x minus 8 equals 0, or 3x minus 8 equals 0. And 3x equals 8, x equals 8 over 3, or exactly the same thing when we get it here. So sometimes when we do this, almost always we get two answers if we get an answer, but sometimes those two answers will be exactly the same thing, like they are here. So in this case, x has to be 8/3, and there's only one answer, but it's a repeated answer. And we're going to find out something interesting about what happens when it's like this in the next chapter or two. So this is called a repeated root, and it happens sometimes when you have exactly the same thing, or when you have exactly what we're talking about here in 8-6. So let's look for another one like that. A squared plus 12a plus 36 equals 0. Let's see. This is a perfect square. It's a squared. Is this a perfect square? So we've got an a squared, and we've got plus 6 squared. Yep. And 6 times a is here. And if we multiply that by 2, do I get that? I sure do. So that means we have our repeated, or we have our perfect squares again. A plus 6 times a plus 6 equals 0. So that means a can be minus 6, or a can be minus 6. So we have our repeated root situation happening again here. So that's chapter 8. We've talked about everything in our book. There are just a few other things, but I think we'll let you just practice your homework and see what comes up. Let me do one more example for you, just because this is fun. Y minus 6 squared equals 81. Now, some of you might be tempted to FOIL this out and then subtract 81 from both sides and see if you can factor it again. And that is a good way to do it. But sometimes there's an easier way, and that's like when it's like this, and all I have to do is take a square root of both sides. You see how this is squared? If I just take the square root here and the square root there, then I will be left with a y minus 6 equals 9. And y equals, if I add 6, y is 15. So there's a shortcut to doing it. And you can only do that sometimes. You can only do that when you have perfect squares. Okay, let's do another example like that. I know I said it was just one more example. You can live with me, can't you? X plus 6 quantity squared equals 12. Again, don't forget, if you've got something that's squared all by itself on one side of the equal sign, you can just take the square root of both sides, and you're left with an x plus 6 equals the square root of 12. And we're going to learn more about what to do with this square root of 12 later, but if we want to get x by itself, it's going to be x equals a negative 6 plus or minus the square root of 12. Plus or minus. That's not something we've really talked about much yet. We'll get to it. Some of you may already know what that plus or minus means. And if not, we'll talk about it in class. Okay? Enjoy your homework. I will see you on Tuesday. Have a wonderful Monday. Good night.